Activity 2.9 through problems 1 through 6 actually involves two separate data sets. So in order to, again, save time and avoid minimal errors, I've constructed a pre-built activity that has both of those data sets already compiled. So what we see is one table with values for x1 and y1, another table for values for x2 and y2. So if we have multiple data sets being graphed simultaneously, we can, for the sake of clarity, go ahead and turn one of those data sets off. So for instance, our values for x2 and y2 won't be used until problem 6. So we can just hide those results so that they're not interfering with the results that we're trying to look at for questions 1 through 5. In this case, the data is plotted, but we're also asked in part 1 to determine an appropriate scale for our viewing window. So we could go ahead and click on that wrench icon and plug in some better values for our maximum and minimum x and y values. So for instance, our x scale could go from 0 to 11 with steps of 1, and our y-axis could go from 14,000 to 23,000 with steps of 1,000. And then if we want, we can click and drag this a little bit if we want to just shift that view a little bit to make sure we see this first point as well. Since the data was already entered, and now we've adjusted that scale, we have everything completed up through question 3, part C, where then we're asked to determine the regression line for this data. So since we have two different tables with x1, y1 and x2, y2, now we just need to be careful when constructing that regression equation to make sure we're referencing the appropriate table. So we want to make sure we're using y subscript 1, since we're using that first table, tilde mx subscript 1 plus b. So in this case, we're still not doing anything with the second table. We're not referencing x2 and y2, so we're just saving that until later. But entering this equation with that tilde symbol gives us the regression equation with our values for m, b, our correlation coefficient, and the residuals if we want to investigate them. But then what we see in question 4, what we're asked to do is complete a table that has the original input, the actual output, and then our model's predicted output. So one way we can do that with Desmos is by going back to our original table for x1, y1, and clicking off to the right here, we can introduce a new table, or a new column, and what we can do is auto-populate that column by entering in our least squares regression equation. So in this case, our value for m and b are already determined, so we can just type this in as that equation, or that formula, m times x1 plus b. So now what we have is a table that's giving us our values, our original input values, the original corresponding data points, and then our predicted values based off our model. In question 5, parts A and B, now we're asked to add to this model. We want to use the regression equation to predict the average tuition and room and board at four-year colleges in the year ending in 2004. And then in part B, we want to do that again in 2015 and 2020. So those would be 3 years, 14 years, and 19 years later. So what we can do is click to add a new row to our table. We don't have a value for x1 is equal to 3, so we can add that in. So this would be giving us the average tuition, room, and board in the year ending 2004, so 3 years after 2001. We don't need to populate a y value because we don't have an original data point, an original corresponding data point there. But this will go ahead and auto-populate what our model would predict. We can do the same thing with what would happen at the end of 2015 by entering a value of 14, and then for 2020 by entering a value of 19. So we can continue to add to that table and make predictions based off our model for any input value. In question 5, part D, we're asked to graph the regression equation on a graphing calculator, which we've already done with Desmos, and use our graph to estimate the year in which average tuition, room, and board will be at least 30,000. There are a couple of different ways we can do this. One would be to sort of emulate the trace feature of a graphing calculator by introducing a point, which we could represent as a comma m times a plus b. So the point you're graphing here is some arbitrary value or some constant a, and then the y-coordinate is being given to us by just evaluating our least squares regression equation at x is equal to a. So we could add a slider, and now we have this point which we could drag and we could increase until we are exceeding values of what we're looking for, 30,000. So in this case we would need to zoom out on our graph a little bit. And in this case we have to go quite far actually. And if we want, we could label that point until we see that our y-coordinate is just exceeding 30,000. So that would give us an x value of about 24.56, or about 25 years later. So we can emulate that trace feature. Another option, if we wanted to turn that point off, would be to simply graph another line, which would be y equals 30,000. If we wanted to, we could change this to a dashed line, and what we'd be looking for is just the place where these two lines intersect. So if we click on either line, we'll see this sort of gray point pop up, which is giving us that actual point of intersection of 24.558, 30,000. So we could use that trace feature, or just use the idea of two intersecting lines to find when that would occur. So 25 years later, or in about 2026. Now we can move ahead to question 6, where now we're using this new set of data, but we want to complete some similar tasks. We want to sketch a scatter plot, which would mean finding a reasonable domain and range or viewing window for our graph. We want to construct the linear regression model, and in part D, we want to use that regression model to predict the number of bachelor's degrees that will be earned by women in the year 2020. So now essentially what we would want to do is go back and turn off anything that relates to what we calculated or what we completed for parts 1 through 5, and turn on this table of values for x2 and y2, which corresponds to what we're doing in question 6. Now initially I don't see anything listed here, because what we need to do first is adjust our domain and range for our viewing window, which we could set to be 0 to 28 with a step of 2, and 0 to 1000 with a step of 100. And then we can manually adjust a little bit if we want. So now what we're looking at is that second set of data values. To construct our regression equation, we would now want to reference y2 and x2 to construct this alternate regression equation. So now we have a different value for m and b. And actually probably what we should do is, rather than use m and b, since I'm not actually sure how it's going to interact when we have overlapping letters there, we could call this n and c. So we still have something in that y equals mx plus b form. We're just using different constants so that when we call on these values, we're going to make sure we're calling on the appropriate values. So now we have a slope of about 20 and a y-intercept of about 539. For the last part of this problem then, what we want to do is go ahead and add our predicted values based off the model to our table, so that then in part D we can predict the number of bachelor's degrees that will be earned by women in the year 2020 by plugging in a value of 30 for our x-coordinate to get a predicted value of 1,140. Or since, according to the context of the problem, that number is actually in thousands, that'll translate to a little over 1 million.